I wanted to share some ideas that have developed. I have a slight philosophical background, but my main background is in computer engineering. And let's say I have been interested in complexity already for 20 years. So let's say I think it's interesting to analyze and discuss how the relationship between science and philosophy has been made over the centuries, in the sense that both science and philosophy are interested in trying to understand phenomena around us and the world around us, but they have slightly different approaches. So science has to do more with experimentation and trying to, let's say, intervene and control nature, and philosophy more about this discourse and how we are able to know and describe the phenomena around us. And in some cases, we might think that they are very different fields, but since they are both about understanding our world, there are deep connections between them, and they affect each other even when, in many cases, we don't realize this relationship, in the sense that advances in science and our understanding of phenomena have impact in philosophy and vice versa. So I want to share what impacts the advancements in the scientific study of complex systems are having in philosophy. So as a bit of a background, science has been traditionally reductionist. This means that since the times of Descartes, Galileo, Newton, Laplace, science has tried to simplify and to isolate phenomena in order to be able to predict them. And this method, that's why it's called reductionism, because you try to eliminate all the unnecessary aspects of a phenomenon and try to get to its essence. This has been extremely useful, and the progress that has achieved, it's quite remarkable. Just the technologies that come from this approach are all around us. They have transformed society. We have computers, we have reached the moon, and also in medicine, using this approach, the life expectancy, average life expectancy has doubled in less than a century. So it's quite amazing, but perhaps this high effectivity has led us to assume that there's nothing wrong with it, or let's say, not so much that there's nothing wrong with it, but that it doesn't have any limits. And that's not necessarily the case. So as we have understand and studied more about complexity, we have realized some of the severe limitations of reductionist approach to science, and also the impacts that this has on philosophy. So we can define complexity with lots of different ways. There are dozens of measures in the literature of complexity in different areas. So let's say it would be a bit naive trying to come with a single definition of complexity, because the word acquires different meanings in different contexts. But let's say to try to be on the same page and to have more or less understanding what we mean by complexity, the etymology comes from the Latin plexus, which means interwoven. And this means that something complex is something which is difficult to separate. So if a system is difficult to separate, it's because there are relevant interactions between the components. And for interaction to be relevant, it means that the future state of the components is co-determined by other components. So in order to give an example to say what this means, imagine you have a friend from childhood, I don't know, John, and you know all the tastes of John. You know what kind of music he likes, what kind of food he likes. So you could say that you know so well John that you have the laws of John, and then you can predict his behavior given the circumstances. Then you can tell what he's going to say. But then you go to university, you enter Stanford, and then suddenly John meets Mary, and they fall in love, and they start going out, and suddenly you notice that John changed his behavior. So he starts listening to different music, dressing differently, taking showers more regularly, cursing less. So if you just stick with your isolated description of John, you will not be able to predict his behavior anymore, and you will not be able to explain why his behavior changed. And of course, it changed because the relationship he acquired with Mary. And suppose that they graduate and they get married and they have a child. The child will not only generate new interactions with the parents, which will affect their behavior, but it will also change the interactions and the nature of the interactions which they had already. So, I mean, this is a very down-to-earth example just to illustrate that in many cases, if we are restricted to the description of an isolated element, then we will not be able to explain what kind of states it will go depending on the interactions it has with other components. And in this sense, when we have interactions, then reductionism is not adequate, because precisely reductionism tries to isolate and simplify in order to predict. And why is this? In high school, we are taught in physics that in order to predict the future of a system, you just need the initial and boundary conditions and then the laws that govern the system. And it works in textbooks, but then in reality, there's always some new information which arises out of these interactions. And since this this information is not in the initial or boundary conditions, our prediction is limited. And also, since complexity is everywhere, then we are, I mean, it's not like it's just some particular aspect of some discipline and then we will find a way of solving it. It's really affecting the way we relate to our world, in the sense that we cannot ignore interactions anymore. And just to clarify, because sometimes the concept of complexity gets confused with complicated. And complicated is something difficult, and the opposite of something complicated will be something easy. And if we understand complexity as something which is difficult to separate, then the opposite would be separable. And also another common confusion is complexity and chaos. Chaos is something which is sensitive to changes. So a small change leads to big consequences. And the opposite of chaos would be stable or ordered. So let's say they are related, and then you can have many systems which are at the same time complex and complicated and chaotic, but you can have all possible combinations of having one of these properties or not. And it's also useful to realize why we are speaking about complexity in our age and not before. It's not that previously people were not aware about complexities of phenomena. If you read Darwin, he's very well aware about complexities in ecology. I mean, ecology studies complex systems and the interactions between different species. And the main difference, I think, is that we didn't have the tools to study complexity until recently, let's say a bit more than 30 years ago. And Hans Pagels describes computers as the telescopes of complexity, in the sense that before we had microscopes, we had theories of agents of disease. Say there was this theory of humors, which cause disease, but before we saw the microorganisms, then we didn't have the proper understanding of the phenomena to fight infectious disease, which came only in the 19th century. And the same with telescopes. With our naked eye, we can see only until Jupiter, and the only satellite we can see is our own moon. And sometimes we forget that just a century ago, our our measuring tools were such that we could, let's say, people thought that the whole universe was just our galaxy. The first galaxies, apart from the Milky Way, were detected in the 1930s. So let's say it's not that long ago that our worldview changed considerably because of the power of the telescopes. And what Pagel says is that computers are tools to study this complexity, because with our, let's say, traditional tools for analyzing systems, which would be differential equations, let's say we are limited to the number of variables and conditions that we can study. I mean, if you want to solve a system of more than 3 variables of differential equations, then you already run into trouble. Now, if you want to study, I don't know, 10 million variables and how they coordinate with each other, differential equations might not be the best approach unless you have computers. So that's why we are studying computers now, why complexity began in the 80s when personal computers become widespread. And also, in philosophy, there's the distinction between epistemology and ontology. Epistemology studies knowledge, so how can we describe phenomena, and ontology deals with things as they really are, so try to be a bit independent of the observer. And when we say that, when we speak about complexity, it is more an epistemological question rather than ontological, in the sense that when we say, oh, this system is complex, we cannot really say that this complexity is an essential aspect of the system, but rather it's a description that we make of the phenomenon. So, for example, we could describe cells as complex systems because they are composed of billions of molecules which are interacting, but we could also describe cells as Boolean variables. In one value they're dead, in another value they're alive. And then we cannot say, independent of a context, which description is more appropriate. It depends on the purpose that we have for making that description or that model of the cell. And the same applies to any complex systems. We can say for any system, oh, this system is complex, or this system is not complex, but this is an epistemological stance. I mean, and anyway, even ontology is epistemological in the sense that when we speak about the things as they are independent of the observer, we're using a language, and the moment we use a language, it's already epistemology. But anyway, that doesn't mean that we cannot speak about it. It means that we can never have full objectivity as we would like in science. I mean, all descriptions are related to an observer, to the context of the observer. And it's useful to mention this because in many cases we can run into discussions which are caused basically because we have different perspectives or different contexts, and we use the same words with different meaning. So what I will propose now is some implications of considering interactions as real, as matter and energy, and I will say why I think we should consider, well, real or unreal, independently of what we define as real. What I mean is that interactions have causal effect on matter and energy, and also that an alternative epistemology to the one we have, which is based on matter and energy, could be based on information. So the first implication of considering interactions as something real or at the same level of reality as matter as energy is that we cannot hold reductionism anymore. Reductionism would assume that the whole can be described completely by the description of the parts, and let's say this view put forward mainly by physicists would assume that if we go to the most elementary level of description, which say nowadays would be elementary particles, but it's not certain whether these elementary particles cannot be decomposed into even smaller components. We cannot do it because the amount of energy we would require to say, smash 2 electrons and see what they're composed of, it's beyond the energy we can handle nowadays. But then reductionism assumes that if we really understand what are the laws of nature at the lower level, then we will be able to predict everything from those laws, which sounds very similar to Laplace's demon, who would say that, well, since particles follow Newtonian mechanics, if there was a demon who had access to the position and momenta of all particles in the universe, he would be able to predict all the future and all the past of all particles of the universe. And from thermodynamics, we know that the past is not, we cannot rescue the past from the present because there's dissipation. What this means that different states lead to the same state. So we are all here, but we don't know which path led us here because there are many paths to reach this place. So that's why we cannot go to the past. And then the limits of going to the future are manifold, and there's quantum mechanics, there's sensitivity to initial conditions from chaos, but more importantly, there's complexity in the sense that the new information which is generated by interactions is not present. So we have something which, let's say, technical term is computational irreducibility, meaning that we cannot reach the future without going through all the intermediate steps. And precisely because the information which will lead us to the future requires to be processed by all the intermediate interactions. And it's not like, let's say, with traditional reductionist approach that once you have the equation that describes a phenomenon, then you have an initial value and then you can get the future value at any point in time. And also the phenomenon of emergence, which in some cases it's also misused and abused and confused. We could say simply that emergent properties are those which are present at one scale and are not present at a different scale. And a clear example of this is the properties, for example, of gold, like malleability, conductivity, its color. They cannot be determined from its atomic properties. Or if we know all the properties of carbon, or of the atoms of carbon, that will not give us information about the properties of a larger piece of matter composed of carbon, because it depends also on the organization of the atoms. So with the same atoms, you can have charcoal, or you can have diamond, or you can have carbon nanotubes or buckyballs, and they have very different properties. The atoms are the same, but the organization is different. And this change of organization, which basically means different interactions, changes the properties at the higher level. And we can call this emergent. And as an alternative for reductionism, we can search for an holism, which is not New Age holism, but it's more simply a view where we consider different levels of description at the same time, because we know that just going to the lowest level is not enough. As Murray Gell-Mann says, it doesn't make sense to describe sheep in terms of quarks. And another assumption of traditional science and philosophy is that only matter and energy are real, and all the rest are epiphenomena. So if we have a physics description of the universe, then that should be enough. And epiphenomena means that it's not really real, but it's just some trick that our mind makes in order to describe a world properly. And this leads to dualism in the sense that if we say that only matter and energy are real, then we need to describe how does intelligence or mind or consciousness comes from matter and energy. And we can't. And actually it's the same with any emergent properties. We cannot explain life in terms of matter and energy because the properties of life depend on the organization of its components. So there's this blender thought experiment that Stuart Kaufman writes in one of his books, I think it's in Investigations. Well, he speaks about putting the whole biosphere in a blender, but I think it's, well, I don't know, some cute baby animal, like a baby chinchilla or a koala. You put it in a blender, and then you press maximum, and the material properties for a moment will not be very different from the moment before you press the button. However, it's not alive anymore. The organization changed. So the matter doesn't change, but the organization did. And if we're not including this organization in our description, then we will not be able to distinguish these two differences. And that's why I say that the interactions and the organization is as real as matter and energy. And another example is with money. I mean, the value of money is not on the atoms of gold or in the molecules of paper or in the bits of electronic money, because we cannot distinguish these components from, let's say, a bill which has certain value from a bill which is already devaluated, or it's a fake bill, or let's say it's already broken and then people will not accept it. So the value of money, it's in social relationships, it's a social contract. And however, money has a clear effect on matter and energy. I mean, all the matter which makes up this building used to be somewhere else, and it got transformed, and now it's here making a nice structure. But without the interactions of money, which is not matter or energy, it's let's say a product of our social interaction, then we wouldn't be able to predict that the matter would find its way until here. Let's say the equations we will have would predict that then the matter would stay in the forest or in the mountain or wherever they grab different components to make this building. So that's why I say that interactions are as real as matter and energy, meaning that they have a causal effect on matter and energy. So if our description of the universe is restricted to matter and energy, then clearly it will be incomplete. So an alternative is to instead of trying to study information and meaning in terms of matter and energy, we can study matter and energy in terms of information, and then we can use the same formalism for all phenomena, and then we don't fall into a dualism. Another implication of interactions is that the world is not predictable. We wished the world was predictable, but unfortunately it isn't. And I mean, there's the assumption that the world is predictable. We just need to find the right laws of nature, and then we will be able to predict. And actually, it seems that the implicit mission of science is to find the laws of the universe in order to be able to predict and control the world for our own benefit. And however, if interactions generate novel information, which is not in initial or boundary conditions, then the prediction is limited precisely because of computational reducibility. And if we cannot predict everything, then we should better be prepared to expect the unexpected. And we can do this with adaptation. So it is desirable to build systems which are adaptive to unforeseen situations. And in my lab, we have used the concept of self-organization to build adaptive systems, in the sense that if you know that a situation will change, but you don't know how it will change because you haven't been there with all the information that interactions will generate, then instead of proposing a solution for a problem which is still not present, you can build the components of a system that will search by themselves through their own interactions constantly for a solution, so when the problem changes, they can adapt. And well, the Platonism is, let's say, not precisely related with reductionism, but they go hand in hand. And basically, what I mean by Platonism is that the assumption that there's a single true description of the world or of all phenomena. And this would mean that once we find a true description, then all others are wrong, and this one will be valid always and forever, and it's unchangeable. And I mean, already Wittgenstein, more than half a century ago, noted that all descriptions are made within a language. Then some postmodernist authors would say, well, everything is relative, so then anything goes. And there's this problem which I call the silly theorem problem, which has to do with Gödel's incompleteness theorems, and also with the halting problem, and also with Chaitin's omega. And let's say, to explain it in a few words, for any silly theorem we can think of, we can define a set of axioms for which this silly theorem will be valid. So I don't know, we could say something like, so we could change the axioms of our mathematics so that this will be valid. One would say, well, what do you mean 1 + 1 is 2, but then in base 2, 1, 0 it's 2, so then this is valid. I mean, it's just one example in the sense that you can make some silly arguments and then you just change the rules of the game and then those silly arguments become true. And then how do you choose which axioms are true? And that depends on experience. But another example, imagine that there's a sphere and the sphere is half white, half black, but we can see only one perspective of that sphere. So some people will see a black circle, some people will see a white circle, some people will see 50%, 50%, and so on. So we could have holy wars trying to convince each other that the circle is black or the circle is white. But we will be all wrong. It's not a circle, it's a sphere, and it's both colors. And if we try to be democratic and say, okay, let's make a poll, and then we'll see what's the average color of the circle, it might very well be that the majority voting for the black for the black sphere are biased, and they're just looking from one perspective, and that doesn't mean that, let's say, the sphere is 90% black, for example, if 90% of observers are looking at it from this perspective. So if we just assume that there is no single truth, but all truths are dependent on a context, then we can allow different descriptions to coexist, in the sense that we can say, okay, instead of trying to convince each other, if we are looking at the same phenomena from different perspectives, which description from different perspectives is the correct one, we just try to take a broader look and realize that we are describing the same phenomena from different perspectives, and then we allow these different perspectives to coexist, and then we will be able to have a better understanding of phenomena, because if instead of trying to convince each other which one is the real one, we try to understand under which conditions it appears to be black or white or both, then let's say we'll have less incomplete descriptions of phenomena. And another consequence of materialism, it's that in some cases it would lead to nihilism. In the sense that if you can explain everything in terms of the laws of physics, matter and energy, then and everything is epiphenomena, then let's say free will doesn't really exist, and then what's the space for creativity and so on. So it leads to nihilism, which is an approach basically that nothing exists, so then there's no value for anything. However, we can see that if information is generated constantly through interactions, then let's say the future is not determined. So there's always space for amazement, and also if we consider the contextuality, then not only new information is generated constantly, but for the same phenomena, we can look at it from different perspectives, and this will generate also new information. So we can find always more meaning in human life and all phenomena, and it's already meaningful, the process of trying to find this meaning. And also another conclusion is that we can consider that free will exists, which is good for different purposes. And then we can speak about meaningfulness in different contexts. So to conclude, I'm not trying to say, oh, well, reductionism is bad. We should stop using it. It's very convenient. It's a highly effective method. But precisely its effectivity has had an impact, in particular in philosophy, making implications which are no longer valid in the light of our current understanding of complex systems. And since we know that no phenomenon is isolated, we can say that everything is related, and potentially there are always novel interactions. So even if we neglect interactions in our description, that doesn't mean that they don't exist. It's just that we are not considering them. And also, if we have broader understanding of different descriptions of the same phenomena, this will lead to less conflicts. And also, it's interesting that the consequences, the philosophical consequences of the scientific study of complex systems are pretty much aligned with Eastern philosophies, the Taoist and Buddhist philosophies. In particular, in Buddhism, it said that the separation of subject, object, and action is artificial, in the sense that you cannot speak of one of these without the other two. But it's very interesting because one could say, oh, well, we knew this already for more than 2,000 years. But we were able to study scientifically complex systems because of reductionism. And it was through reductionism that we came back to realize the value of interactions. Because in traditional philosophies, we would just say, let's say, Eastern philosophies and also some Native American philosophies, you say, well, yeah, everything is related. But then if everything is related, then there's not much you can do, you cannot analyze. And it was through reductionism that we were able to understand components of systems. And then it was thanks to reductionism that we were able to build computers, and thanks to computers that we are now able to understand complex systems in a way that was not possible beforehand. So I think it's time to change our worldview, which is not, I mean, we cannot have reductionist approaches anymore. They're simply not consistent with our understanding of the world. And I think it's important to speak about this because in many cases, if we are just focused on our own discipline, we sometimes forget about the implications of the descriptions and of the tools and of the language we use, which are changing. So I just would also like to invite you to subscribe to Complexity Digest, which we've been editing at the university already for 10 years. Before, Gottfried Meyer was the editor since 1999, and let's say you can follow us on Twitter or just subscribe for free. There's a weekly newsletter with the latest research related to complex systems. Thank you. Yeah. Questions?
Sure. Do you mind going back to the slide, the non-flip on?
Yeah.
Oh, sure. Yeah, so what year did the Wittgenstein kind of description come out?
Yeah, so let's say people describe as Wittgenstein having two phases. In his earlier years, during the First World War, he was writing his Tractatus Logicus Philosophicus in the trenches. And basically, he built a formal system, and the conclusion was that you couldn't speak about philosophy, so you should better not speak about it. But so some people say that he killed philosophy. But then after some years, he was a teacher at an elementary school in some little village, and also I forget already the particular aspects of his life, but later he would write notes, and they're compiled in a work called Philosophical Investigations. And he basically flipped his worldview completely, because he realized that based on logic you couldn't describe or study properly linguistic phenomena. So, I mean, the structure of all of his works are interesting because it's not like a usual text, it's just like phrases or quotes or musings. And in philosophical investigations, he basically is, I mean, it has certain structure, but in many cases just like, oh, I wonder what happens with this and that. So one of these has to do, for example, with synonyms. So like, oh, well, there's bank, but then it could be the bank of a river, or the bank where you put money, or well, in Spanish, it's also a bench, it's also bank. So here's saying, well, how can you distinguish the different meanings of the same words? In the sense that if you declare it with propositional logic, then it's difficult to formalize the natural language. And it seems that he realized that you can't. Simply, it's not possible to completely formalize natural language. Yeah.
It's very interesting. I've been reading a lot of Sean Carroll, and he put forward a kind of a framework that he calls poetic naturalism. I don't know if you're familiar with it,
Nope.
But it's basically very similar to this. It seems like it might be after or based on this.
Yep.
But it's the idea that you basically, when you describe something physically, you choose the story you're going to tell
Yep.
and kind of the context. So you could talk about a table at the scale of the table, about
Yep.
its material properties and how it might break under certain loads. Or you could alternatively and equally validly talk about the molecules it's composed of.
Yep.
And kind of move up the scales in that way. And they're both coexistent. So I was just kind of curious if those were more or less the same thing.
Yeah. I think they're related, and also in the social sciences and humanities, there's a tradition of speaking about narratives, and because it's very clear that if you tell a story of, I don't know, Second World War, it will be a very different story depending on how you tell the story. But then it was assumed that in physics there's just a single objective description of physical phenomena, and then that's the reality, and then let's say if you have a different description, then it's wrong. And we are realizing that what we call the laws of physics are also descriptions and models that we have, which are convenient to use in the sense that the law of universal gravitation is not valid for microscales or macroscales, but it's convenient at many scales which interest to us, and we make buildings and rockets using these equations. But that doesn't mean that they're real or true or something. They're valid within a context, which is useful in many situations. But that doesn't mean that, let's say, they're more than just a description. Yep. Yep.
We have time for more questions.
Thank you. I really liked your distinction about complexity being somewhat contextual.
Yep.
And it seems that within complexity sciences, we have a more a group or a thought that it's more ontological than
Yep.
epistemological. And I thank you for pointing out that distinction. But I would like to, because I'm not perhaps as well versed in this, if you could describe what that ontological stance is, because I've never really got it, and I've always been suspicious about it, but
Yes.
I'd love it to be clarified a bit.
Yes, personally, I don't think that we can make too much statements about ontology, precisely because the moment we speak about it, it's already in a language and it's already an abstraction. However, building on Buddhist philosophy, let's say in Buddhist philosophy, what they consider real is something which is not changing. So then if it doesn't change, then you can say that it's valid always. And then you start analyzing things and they say, well, everything changes. But then what doesn't change, it's not phenomena themselves, but the potential of phenomena. So I think that in a way this could be interpreted as information, in the sense that information not as ones or zeros, but the potential of having ones and zeros. So when you speak about, oh, well, there's the potential of anything coming in here, then everything is contained in that description, and that doesn't change. But then it's so abstract that it's not so practical. And at the end, let's say you can speak about it and say, okay, this is something very abstract and that doesn't change, and then you could say that that is real. But then again, since you are describing it and it's epistemological approach to ontology, then someone could have a different perspective and say, oh, no, matter and energy are the real things. And then you cannot say, independently of a context like, oh, no, I'm right and you're wrong. So let's say the problem about ontology is that the only way of accessing it is through epistemology, but ontology tries to free itself from epistemology, but you can't. Yeah. There was another question here.
So on Wittgenstein, he denied that he had two phases in his work. That was something that Russell claimed, whereas he thought that people misunderstood his early work and thought it was simpler than it was. In the question of various people in philosophy come to similar conclusions, as you said, different traditions do. So there's not one strand, but if you go back, like the Tao, which can be named, is not the Tao. So that's the same kind of insight. So you see it over and over again. It's just very hard to build on. So it keeps being rediscovered.
Yeah.
On the ontological epistemological question, another way of distinguishing it is saying, are the limits of reductionism ontological or epistemological? If we had, universes full of computers and we had all the information in the world, then could we eliminate complexity? Yeah. Or is there something beyond that?
Yeah. I think these thought experiments, actually they're related to Russell's paradox, which, well, maybe I shouldn't go into the details of that, but basically,
whatever you want.
But basically, if you would try to simulate inside a computer the whole universe, then that simulation should contain itself. And since we assume that that computer is a subset of the universe, a subset of the universe cannot contain, let's say, a larger set and then itself again. So in principle, it wouldn't be possible. In theory, it is, because Turing machines have infinite memory, but in practice, they don't. So let's say we are limited just by the finite nature of the world.
All right, last question.
Yep.
Yeah. So regarding your comment on the relation between complexity and free will, so do you think this is like there's a real connection between complexity and free will, or maybe just complexity because of some issues of non-predictability allows a space of discussion about free will? But do you think there is a real connection there?
Yeah, I think free will is another example of an emergent property that, let's say, it cannot be reduced to the components, let's say, in the sense that even if you have the full information at the lower level of an individual, let's say all the information of my cells, that wouldn't be enough to predict what would be my next action, whether I would raise this hand or that hand. There are some, we'll say in neuroscience, there are some interesting experiments. So for example, if I decide to raise my hand like this or like that, then like 1 or 2 seconds before, there's a signal somewhere here before I realize that I want to do it. So let's say some, I think it was Wolf Singer or someone was telling me that it would be a bit of well, it would be a bit of a cruel experiment for subjects to to have some sort of sensor detecting when they're going to make some supposedly voluntary movement, and then to get a signal before they realize that they want to do that movement, because you can detect it before one thinks that, let's say, one realizes that one wants to do that thing. But I think the fact that you can predict for 1 or 2 seconds before doesn't mean that you can predict, like, oh, what will I do in 2 years or tomorrow. Because these decisions are products of constant interactions at different levels. So if you cannot reduce to the components, then there's the space of which we call free will. And maybe we could call it with a different name if it's less problematic. But let's say for social purposes and legal purposes, we can say that, let's say, we should be held responsible for our actions. I mean, that's the big problem of the discussion of free will. If there's no free will, then it was not my choice. There was nothing I could do, so then I had to kill or not that person. And let's say, there is always choice. Yep.
Okay, let's thank Carlos
Yep.
again.
Thank you.